I want to try to do a better job explaining phase shifting, and I think I've got it. We'll see how you feel afterwards. Maybe you'll understand it less than than the other day. And so we'll back up again, and instead of having a circuit with an on-off switch, it actually shows the function generator. But let's go back. We'll back up a little bit, and we'll see here that we have, and I wanted you to notice, and I showed you both the inductor and the capacitor. We're going to stick with the capacitor at first. Now, the thing to notice about the capacitor and up above is the voltage. I suppose I should have labeled it. This is the voltage, and this is the current. And you have these as part of the pack I gave you if you wanted to cut these out and paste them in. And to be fair, exactly, the one on the left is, and I can show it to you with my USB oscilloscope. This one here is I'm measuring the voltage across the capacitor directly. And here, on the lower one, I'm measuring the voltage across the resistor. So V out is delta V capacitor, and here V out is delta V resistor, but that is essentially equal to the current I total, which is then equal to the delta VR over R, right? Because it's a series circuit. We have and this is, some of it can only work when we're talking about a 2-element voltage divider, and let's make it generalized, little boxes, right? So it's a 2-element divider. It's in series. The circuit elements are in series, so we know they all share the same I. And as I mentioned, and I'll get back to it again, that resistors turn currents into voltage. So if we charge a capacitor, we notice that instantaneously its voltage is 0 and it climbs, but its current is maximal and it declines. So you would say that the voltage lags behind the current. V lags, if you like. So when I apply a voltage, immediately the current reacts, but the voltage takes its time. And everything has the same time constant. It's just the same, see, 15K, 15, 15. You're just rearranging them. And it's put in to brackets because it's the magnitude. And remember, of course, it's frequency dependent as well. It's not that critical just yet. Now, one thing I didn't talk about, and we try to stay away from math, is that when you do the calculus, you end up with this equation, and you get the phase shift. We're just dealing with the empirical evidence that we see something going on, right? And I'm explaining it to you because in the way I'm explaining it to you is that there's this negative sign here. Now this diagram is really hard to understand. And I was thinking about how can I patch it up, but I came up with a different way to explain the whole thing. But I want to start with this and segue into the better explanation. So what they generally tell you is like, This is V in a way. The I, because if you think about it, the I is common to everything. And what a capacitor does is that it splits the I and the V, and they're 90 degrees apart. Now, they call this the phase angle here. That's not correct, what they point to here. The phase angle would be, well, I don't even want to get into it right now. But there's a 90-degree split. And we're going to learn eventually that if I had an inductor, the inductor would point this way. But right now, we're going to just focus on capacitors. And so you see with the 90-degree phase shift, and if you think about it, if I turn on the switch, instantly the current is high, but the voltage takes time. So the voltage lags behind. So now let's take a look over here. So it's this same here. And now, once again, I'm measuring the voltage across the resistor. That's V out. And it looks perfect, right? I noticed that the V out, the current, is lagging behind the V in. However, if you look to the left, we would expect that the peak of the voltage across the capacitor, we should see zero current, and we don't. Well, that's because we can't measure the voltage and the current in the capacitor. We could, in principle, put an ammeter there, and the problem is an ammeter gives you the integrated signal. It doesn't tell you the details, right? So you wouldn't you wouldn't be able to measure the phase shift. So voltmeters and ammeters, we mostly use them with DC, but they only give us an average value, an integrated value. The oscilloscope gives it to us in real time. So the existence of the resistor says that the phase shift there isn't exactly 90, but in the capacitor is having an effect. So notice that this is a high-pass filter. And remember 2 pi FC. And we are at 500 hertz, which is a fairly low, somewhat low frequency. So that means that the capacitor has a high impedance at this point. And it makes sense because then it tells us that since the voltage, the V out is less because the Z1, remember our voltage divider equation, the output, right now Z1 is greater than Z2. So V out is less. But when the capacitor Z is high, that's when you see the most phase shift. And that goes back to now the better way to look at it. Oops. Maybe I'll go back to this just for a second. You see, in general, the phase shift phase is directly proportional with Z of C. So when Z and C is large, you expect to see more of a phase shift. Because what happens is the phase shift is a combination of the contribution of the capacitor and the resistor. And remember, these diagrams are available in the printout if you care to cut them out and paste them in. Or you could do it later because you could watch this recording, right? Maybe just leave yourself some space. Okay, so let's take a look. So once again, we're looking at this. And you notice now I have the Z of the capacitor in red, the Z of the resistor is in purple, and the Z total is the Pythagorean the Pythagorean sum. Say that 5 times fast. Now, remember, we saw that fancy diagram before. What we see in the real world is the projection onto the real axis. Remember that fancy rotating diagram? And the real axis is left and right. So this thing is rotating, and as time goes by, it rotates counterclockwise. So the V in is the voltage across Z total, right? Because our rules of circuitry tell us that the voltage of the power supply has to equal the total voltage across the circuit. Now notice that Z total, when that's fully projected onto the real axis, that's here where this dotted line is. Notice that the voltage across the resistor, because that's what we're looking at. V out is the resistor, and its projection is smaller. And as this thing is rotating, it's getting even smaller. So the reason I gave you this slide is because you can't rotate this. So right now, if I put this like this, so I'd imagine you could paste this guy here like in the middle of the page and then paste these things at different angles around it. So this point now corresponds to right here. We have the Z total maximally projected on the real axis. And we see that the ZR is then smaller, which is V out now. At the moment, because we're using the high-pass filter, this is V out. And it's smaller, and if I keep rotating this, so when it's at this angle, and I just had an inspiration, copy. Now, if I rotate it like this, and you'll see the red and purple aren't exactly at right angles, forgive me. This corresponds to when V out equals to 0 right here. Because the voltage across the resistor is maximally projected onto the imaginary axis. But you see then that the this happens first, the red one happens first, and then the blue one is always playing catch up. Even though in our minds we think we're applying V in, right? It makes it hard to imagine. How can something happen in the past before we even did the cause and effect? Well, that's because it's a continuous signal, right? So it's not like it just started on the left. We trigger it at a certain point, but it's been going on. We're just sampling it, right? So when you look at the oscilloscope, things that are earlier in time are on the left. So the V out across the resistor is behind. And you can see it, right, it happens first. Because remember, this thing is rotating counterclockwise. And by the way, does everybody know, I don't know if I explained this or not, does everybody know why the positive angles are counterclockwise? Do you know about how to define a right-handed coordinate system? I cross J equals K. So that means that a right-handed screw, if I do I cross J, then the Z vector comes at me. Well, think about it. That's why the Z axis would be pointing up at us, and that's why counterclockwise is the positive direction of rotation. Did you know that? Now you do, right? I don't know if anybody told you that before. I'll draw it out another time. Good. I'm glad you got some exposure to linear algebra. When I was a student here, we had a professor, Bradbury. We only had to take 1/4 of mathematical physics. I took 3. He was amazing. Anyways, and then you could keep going. So let's copy paste this again. And I could rotate this thing even more. And now we would say that V in is equal to 0. And so this corresponds to this point right here. V in is equal to 0. And the projection of well, we don't know the voltage of the capacitor because we're not measuring it. But notice that the projection of the Z of R is on the negative real axis. And there you see it's negative, and if I keep rotating, it's going to get a little bit bigger. It's still right here. It's still going to get a little bit bigger when it points maximally along the negative real axis. So isn't that so much easier to understand, right? Even Hayes didn't make it that far. So then if I go ahead and increase the frequency, now the Z total approaches ZR because now this is at 2500. Z capacitor has become smaller. Ironic. Oh, I think I gave you this slide. Z capacitor has become smaller, so now Z total is mostly ZR. And I'll bring this back. Just let me copy this. So now the Z of the capacitor is no longer close to the R. It's much less because I'm at higher frequency. And notice that the V out over V in has become nearly equal, and the phase shift is much less. And also, I make sure to point out, since we're measuring ZR, ZR comes earlier than Z total, and that's why V out is before V in. And you have to be careful. This is for the high pass filter. Does anybody need me to back up? We're all good. Okay. Okay, can I go to the next slide yet? Everybody? I know, I see Michael still writing. You got to speak up, Michael. We're going to teach you to be assertive. You know, we're not going to dwell on the fact of how smart we are. We're going to make the assumption we're all very smart because you wouldn't be here if you weren't. And so that means that you have every right to make everybody slow down as the next person. Okay? Because, see, this way, if you don't pass the class, it's your fault, not mine. There's always a Machiavellian catch, right? No, but I mean, it takes time, right? It's easy for me. I was just like you. You know, I'm 65 and I have a PhD, right? I mean, I don't give a fuck anymore what anybody thinks of me or if I raise my hand, right? But it takes. But you need. I learned in life when I developed the attitude that I belong here and I have the ability to raise my hand and interrupt and without feeling like I shouldn't be here. Then life gets better. I mean, as a person of color, I understand some of the nuance there, right, which we can discuss another time. But in this class, we're going to practice behaving as if we're all on the same plane, right? Okay. I hope I'm not being rude to you. Okay. Thank you for that. So now, look carefully. Now we're measuring the voltage across the capacitor, right? V out is, and now the capacitor is Z2. We're at low frequency. We're back at 500 hertz. So Z of C is high. 1 over 2 pi FC. And notice how the red vector, the red component, is bigger than the R component. Also notice that V out is larger, right? Because it's higher at that point. These are both at 500 hertz. One is across the resistor and one is across the capacitor. So now we see that when V in is at a maximum, when the Z total is projected across the real axis, maximally projected, now the voltage across the capacitor is lagging behind. And there it is. And notice it's positive and it's a little bit less. And it's going to increase. It's right here. It still has a little bit ways to go. So this diagram, and let's see if we can be a little clever and make some room for ourselves here. This diagram corresponds to that point. And let's see, what's next? We can say that copy and paste. So if we rotate forward in time, let's look at when the capacitor now has its maximum voltage. V out is the maximum. And that's not very good. Let's undo that. So this is 1. And so this is position 1. And this is position 2. 2. That's a little more easy to understand. So we notice that the capacitor now is at its maximum value. The Z total is before it in time, still before it. And it's beginning to get smaller and it's going down because it's headed towards the imaginary axis. So it's just the same behavior. It's almost completely the same, but notice now that the phase shift is to the right. And that's just because now we're measuring delta V here. And the delta V is behind. The behavior is the opposite with inductors, but we'll get there eventually. And then the really interesting thing is when you put them both together, the capacitor and the inductor. So I put these here in case you wanted to cut them out and put them at different angles and point to this trace for your own edification. And then we put it all together here. Now you see how on the left side is delta V across the resistor and equal to V out. And this is, well, whoops. Copy. Paste. So for the low pass, it's delta V across the capacitor. And now you can completely understand the phase shift, why it's where it is. And the last little bit was when the Z of the capacitor is small, then the phase shift is small. It just depends on whether it's a high pass or a low pass. If it starts far away and from the right and it goes left, or if it starts to the left and goes right. And now, gosh, that was not that hard. Well, it took me a long. I was like letting the smoke was coming off the top of my head today. I was determined. I've been in here since like 9 o'clock this morning, and I had to make it work. Because Feynman said that we don't truly understand that something until we can reduce it to a freshman lecture. So it's always been my mantra that I understand things better when I can do that, and that's why he always wanted to teach. He was offered a position at Princeton, and he wouldn't have had to teach, and he didn't want it. He always wanted to teach, and I've only just been a professor a few years now. It's a gas. On top of, I have a lot of fun doing it. I hope you notice, but a lot of it is because I'm deepening my own understanding. But I just feel like everything should be able to be put into bite-sized slices, other than like cutting-edge theory, which I was discussing a bit with Christian earlier. And at that point, it's not easy. But these sort of things can be broken into simple ideas. All right, so good. I'm going to stop this.